will not eat 5% of my battery. So logs and modeling, here is the goal. First off, we need 2 points. I can find the equation of any function from 2 points. Now, first thing I'm going to do is help you to understand how to find those 2 points using the information about your object. The second thing I'm going to do is show you how we can find the equation using exponential functions. And the third thing we're going to do is find the inverse of the exponential function, which then is going to be our log function. So it's a 3-step process. The first step is a lot of background understanding carbon dating. So for this first process, it might be better for you just to listen intently rather than write a lot of stuff down, because I'm trying to help explain some things to you. All right, so I need 2 points. Let's say first off that I have an object and that I want to try to figure out something out. So let's say that I have an object. And let's say that I know that that object has 100 grams of what's called carbon-14. Now, here's the thing. Everything that has carbon-14 has a beginning amount of carbon-14. So for instance, I know that all living things have about 1.032 times 10 to the negative 12 grams of carbon. That's a real easy number to work with because all living things that you would have chosen for your mobile have that same amount. So remember, if you have I don't know, a dog hanging from your mobile that's like a picture of a dog, you're treating it as the real thing, as the real dog. So I want to make sure that that living thing is the thing that I take carbon-14 dating for. Yeah.
I do have a question. What about a coffin? Because it's made of wood. Trees start out living.
So I would need to know, wood has a different amount of carbon-14 based upon when it's cut down than when it has been there for a while. So if you want to base it on when it's cut down, you just use the living things.
Okay.
Yep, because that would be when it's first created. Good question. Now, if you have an object that is not living, that's fine. I have a list of how much carbon-14 is in each thing when it's first created. So if a rock is created from magma cooling, I can find out A, if that rock actually has carbon-14, and B, how much it would have. Does that make sense? Cool. So let's say I have an object, 100 grams carbon-14. Now, the idea is we need to make sure that we choose an age for this object if it represents a culture of our choice. So let's say I have the Inuit culture back there, and I want my object to be 200 years old. I need to know how much carbon would be in that object after 200 years. Now, we could go through the really long calculation, or we could just use a calculator that I found online that tells you how much carbon something has if it's X number of years old. So on Echo right now, I would like you to go to your project resources, if you have not done so already. And I would like you to click on the link that says Carbon-14 Calculator. Carbon-14 Calculator. Yeah, that's it. Thank you. I'm going to make sure that I can get to it as well. And you had a question, Aisha, would you? Oh. I'm going to do it too so we can just be on the same page here. This is actually part of the workshop that takes the most time today because I have to explain how to get our points. Okay. Recorder, mobile, project resources, carbon detector. All right. So this is what you all see on your screen. Let's say I want my object to be 200 years old. In the first box here where it says years, I'm going to click there and I'm going to type in 200. Now, if you type in 200, what it's going to tell you is it says carbon-14 left equals 97.61%.
Is that just half?
So this means that after 200 years, I'm going to have 97% of the carbon I originally had in the object. So how much of it has decayed?
200.
2.4%.
Yeah, about 3%, 2%, something like that. So really, with respect to carbon, is 200 years a long time? No, because I still have 97% of it left. Okay? So here's something that you need to keep in mind. When I'm doing carbon dating, I think of something called a half-life, meaning that after so many years, half of what I had has decayed. And then after the same amount of years, I have another half that's decayed. And the same amount of years, another half that's decayed. The half-life of carbon-14 is 5,730 years. It's a very long time. It takes that many years for half to decay. So if you have a civilization that has been around for 5, 6, maybe 10,000 years, you can still carbon date. Because carbon dating works up to about 8 or 9 half-lives, which is the equivalent of about 50 to 60,000 years. Okay? So for my object, I know that after 200 years, I have 97.61% left. Now, here's where you need to keep something in mind. 97.61% is a percent. It's not an amount in grams. Here's my starting amount in grams. If I want 97.61% left, how many grams would I have left?
97.
Yeah, for this example, it's easy, because I chose 100 to be my starting
But
amount.
I like 600.
I'm sorry?
It looks like 600.
Well, you know it's 100, because I said it out loud. Here it is. So I have 97.61 grams after 200 years. Now, if I had 5 grams as a starting amount, how would I find out how much 97.61% is? Yeah, I just multiply it by 97.61%. Okay? So that means that our first point, for me at least, is going to be the amount of carbon, comma, the time. So my first point is 97.61, comma, 200. My x, my y. Now, that's actually the hard point to get. The last one's really easy. If what I'm doing is modeling the amount of carbon I have over an amount of time, what is the easiest amount of time to deal with?
1.
Even easier than 1.
100.
Even easier than 100.
0.
0.
Wow. Well.
After 0 years, how much carbon do I have?
So 97%.
100.
100, my starting amount. Yeah. So my next point is going to be 0, comma 100. Or sorry, 100, comma 0. Because this is my starting amount. At time 0, I have my starting amount of grams. So for Charles' example here, for his coffin that he's using, if it's made out of wood, well, it'd be like the minute that wood was cut down and assembled to make a coffin. That's 0.
Is it still going to be in grams or kilograms?
Always in grams. Always in grams.
So how would that work with the 3D printed object?
You're using the object that that object represents. Because obviously you wouldn't have a 3D printed something. It's representing some type of like fossil, some type of living organism, some type of thing that was created. So you're basing it off of what the actual item would have been created by. So if your actual item would have been made out of wood, you would go with wood. If it may have been out of like pottery, ceramics, you would use ceramics. All right, so are we okay on the 2 points? Great, now it's easy because it's the math stuff. Okay, so I have my 2 points. Second step is I actually want to create an exponential equation. Okay? So these points are a part of my logarithmic equation. To find the exponential equation, an exponential is the inverse of a log. So what do I have to do with my points? Flip them. So that means for an exponential equation, I'm going to have 200, comma 97.61, and I'm going to have 0, comma 100. All right, all I did is I flipped these because I'm looking for the inverse right now. Now, the reason why we do this is because it's going to be a heck of a lot easier to find the equation of an exponential and then find the inverse to find the log equation than it is to find the equation of the log outright. Also on the rubric, I asked you to find both equations. This is the easiest way to do both. Okay? So, now I have to remember back from our curling project, those students who were here last semester. An exponential equation has the format f of x equals a times a to the x minus h plus k. That's an exponential equation. Now, I'm going to help you be able to find the exponential equation without any work at all. You just have to think about your information. Okay? So, let's think about this. If I am dealing with things that decay, can I ever have a negative amount?
Yeah.
No. So that means that I'm probably going to have an asymptote at the line 0. So does that mean I've had a vertical shift?
No, so there's 0.
No vertical shift. So again, if I think about the graph of this exponential equation, I'm going to have an asymptote right here on 0 because that's where everything decays to. I can't have a negative amount of something. So that means I have no k. Right? Now, h. What does h do?
Vertical. Shift.
Shift horizontally. In this case, the horizontal number is the amount of grams I have. Am I adding an additional piece to something, or am I just dealing with it as it is? As it is. So do I have a horizontal shift?
No.
No. There's no h.
So what are we left with?
We're getting there. We're getting there. Okay, now, if this exponential function is representing how much I have over a certain period of time, my starting value is going to be what number?
0. The year
With
you
respect to
started.
how much I have of the object.
The year.
In my case, it's 100. It's whatever I start with. So that means that after 0 time, I have 100 grams of my object. Well, that happens to be my A value. Because remember, when I compare it to the parent function, my point right here is normally at 0, 1. I've just amplified it 100 times. Because instead of starting with 1 gram, I'm starting with 100 grams. And now I think I actually have the equation. So I have f of x, there's one piece we have to understand here, equals 100 times. Now, this little a value we call the what? The base. Now, if I'm dealing with half-life, that means that each time I'm cutting the amount in half. And then I cut it in half. And then I cut it in half. So what is my little a value?
1/2.
1/2. Because it's half-life. I'm taking half each time after 5,730 years. So in reality, your equation is going to look the exact same as this one, except for one number is going to be different. What number?
Starting value.
This number right here. It's going to be how much you start with, how many grams of your
So we don't have to do the work like the blue work?
No, I'm helping you to understand where it comes from. That's what I'm doing right now. Okay, so this is the main thing. Good. I'm glad we're making connections. Good. All right, now, here's what I want to do. I want to be able to now find the inverse of this. Because this is my exponential equation, but my inverse will give me my logarithmic equation. So let's go ahead and finish this workshop. We're almost done. I want to find the inverse. This is where the previous lessons come into play now. The first step in finding the inverse is to do what with my f of x and my x?
Switch them.
Switch. So this means that I have x equals 100 times 1/2 the y. And then I solve for y, because x is already by itself, right?
Oh, yeah.
Solve for y. All right, this is where we use some information with respect to properties of logs. Okay? First step is I want to get rid of this 100. How do I get rid of the 100?
Divide by 1.
Divide. So divide by 100. Divide by 100. I have x over 100 equals 1/2 y power. Now at this point we're stuck. We have two options, and this goes back to Friday's journal question. Either I can take this and I can put it into logarithmic form, or I can take what of both sides?
The y thing. Multiply by y.
Yeah, the natural log. I can take the natural log of both sides. That's going to be easiest to do, people, so that's what I'm going to do. So in this point I want to get the y by itself. So we're going to go ahead and take the natural log of the left. We're going to take the natural log of the right. So we have the natural log of x over 100 equals the natural log of 1/2 to the y. Now again, we want the y by itself. What property of logarithms can we use to get the y by itself?
Put it to the front.
Yeah, it's an exponent, which means we can bring it out front. So my next line of work here, we have the natural log of x over 100 equals y times the natural log of 1/2. And then what's my last step?
You divide both sides by the natural log of 100.
Yeah, divide both sides by the natural log of 1/2. And my y is going to be this whole thing. That would be a very challenging equation to find if we had just done it from 2 points on a log function. So I'm going to go ahead and state here that the inverse is this whole thing. Okay. Now, if I would have directly changed that exponential to the logarithmic form, I would still have an inverse. It would look a little bit different. It would be equivalent. It would be the same. It would just look a little bit different because it's a different type of process. If you follow this process to get this inverse, that covers all the standards I'm looking for with respect to graphing your model and the inverse. If you want some extra credit though, under the Project Resources tab, there is a link that says finding the equation of a log function from 2 points. So you would avoid using an exponential, and you would use a process that I've screenshotted for you to find the equation of your function from 2 points. Really, it's just plugging and chugging x and y values into some really large formula to find out what your equation is going to be. It's going to look different than this, but it'll still work.
How many extra credit?
Enough. So if you want to try that for extra credit, if you have time, you're more than welcome to, but that is not something that is required. So again, under the Project Resources tab, it says finding equation of 2 points, logarithmic functions. You're going to follow that process and show me separate work. Make sense? Cool. That ends our log modeling workshop.